Hello and welcome to another live stream from Chemistry 222. My name is Travis. I'm a tutor at the Portland State Learning Center. And to start things off, I just want to share a few links as I always do. This is for the Learning Center's website as well as Facebook and Instagram feeds for them. Definitely follow them on Facebook and Instagram so you can get live updates of any type they have. You should be able to watch these live streams and any additional live streams that I do personally through the following link there, which is my Pinji room. You can also see that link at that side, the bottom of my screen. And you can see any past videos we did, that's including Chemistry 221 as well and Chemistry 222. On the YouTube channel at the Learning Center there. So definitely check out the playlist that we have there. There should be a playlist for each course and continuing on into Chemistry 223 hopefully. So let's get started. Today we're going to talk about reaction rates and kinetics. So we're going to talk about the equation for the rate equation, the rate orders, the different types of rate orders they have. We're going to move that along into activation energies and other fun stuff like that. Mainly chapter 12, the kinetics chapter in your book, up to 12.5. So let's get started here. This first problem here, how will each of the following affect the rate of reaction? So here we have CO gas plus NO2 gas, which is going to create CO2 gas and NO gas. And they say if the rate law for the reaction rate is K times NO, the concentration of NO2 times the concentration of CO. So that's the concentrations of the two reactants at times that K value. K is going to be the rate constant. So it's a constant at different temperatures basically for what that rate's going to be. And we can notice that the exponent that each of these is brought to is the first power. So those are going to be first order reactions. So for the first part A, increasing the pressure of NO2 from 0.1 atmosphere to 0.3 atmospheres. So one way I like to do these problems is to figure out the ratio of what's changing and then multiply that in to find out what that will be on the end of the day. In this case, so that means that I would take that 0.3 atmospheres, I would divide it by 0.1 atmospheres. I can see that I'm increasing the pressure of NO2 by 3. So then how do I use this to determine what that does to the ultimate rate law? What's happening? How does it affect the rate of the reaction? Well, I know the initial rate, I'm going to put rate naught, is going to be equal to K times the concentration of NO2. I'm going to put a little 0 down there. That's before I've changed that pressure. So that's the initial pressure, and then CO initial as well. So now I'm changing just the NO2 pressure, and I'm changing it by a factor of 3. So I can put, basically, I like to rewrite this equation as, say, alpha, which is going to be my answer to how it's going to change, times my rate, the initial rate, is equal to K times, and I put parentheses here, 3 times the initial concentration of O2, because that's what we're doing. We're multiplying that initial pressure by 3. Oops. O2 initial. And then multiply that by the concentration of CO gas initial. And the CO gas isn't really changing in this, so we don't really need the initial, but it's all those initial rates plus I'm multiplying in what's changing. And then I can solve everything based on that. And the reason why this is important is if this was a second order equation, so that was squared, we would need to make sure we squared that 3 as well. In this case, it's a first order equation, so it's a pretty straightforward thing where the initial rate here, we can substitute in on this side. I get alpha times K, concentration of NO2, concentration of CO, it's going to equal K times 3 times concentration of NO2 times the concentration of CO. And notice now I can just cancel pretty much all of those values out. And this tells me that my alpha is equal to 3. So that means my rate for this new equation is going to be 3 times the rate of the old one. So at that new pressure, it's going to be 3 times the rate, essentially. So by increasing this, we can say it's going to increase proportionally because that's going to the first power. Looking at part B, increasing the concentration of CO from 0.02 to 0.06. Really, that's going to be the exact same thing as what we did up here. It's just now, instead of the 3 being here, it's going to be over there. So I can go ahead and just copy this. Paste. Because like I said, it's exactly the same now. The only difference is that 3 goes away. And it's going to move over here. 3 times that. And it's equal to that alpha rate. And again, the rate is going to cancel out the same as before, leaving alpha equals 3. So again, the new rate is going to be 3 times that because we've increased the concentration of those gases, just the same. Let's jump ahead to number 18. In this one, a radioactive phosphorus is used to study biochemical reaction mechanisms because phosphorus atoms are components of many biochemical molecules. The location of phosphorus and the location of the molecule it is bound in can be detected from the electrons or the beta particles it produces. You'll learn more about that in 223 when we start talking about radioactive decay. Here's kind of an example of it where phosphorus 32 will actually decay to losing electrons to, is it strontium? No, that's sulfur. Ooh, that's sulfur 32. So really the only thing that's changed is it's one of its neutrons has turned into a proton and it's lost its electrons. That's that radioactive decay. But it gives you this rate down here. The rate is equal to 4.85 times 10 to the negative 2 per day times the concentration of phosphorus 32. So they want to know what is the instantaneous rate of production of the electrons in a sample with phosphorus concentration of 0.0033 molar. So this is really the equation we need to use to determine the instantaneous rate. And all we really have to do is plug in this concentration in here for phosphorus. And since it's a first order type of equation, it's going to be specifically just that. So we can say that the rate is equal to 4.85 times 10 to the negative 2 per day. I like to write them like that, times the concentration of phosphorus. So that's 0.0033 molar. So I can say 4.85 e to the negative 2 times 0.0033 molar gives me 1.600, say 1.60 times 10 to the negative 4. Oops, my calculator jumped over on me. 1.60 times 10 to the negative 4 per day. Oops. And that's molar per day. So that's how much the concentration is changing per day, essentially. And that's going to be my final answer on this one. So number 22 is a little bit more interesting. Now, under certain conditions, the decomposition of ammonia on a metal surface gives the following data. So what they've done is they've collected the concentration of ammonia at different states and what its rate is. And we want to determine the rate law, the rate constant, and the overall order for this reaction. So the rate law is usually something along the lines of the rate is equal to some constant K times the concentration of NH3 to some order. I'm going to say M in this case. So you have to figure out what that order is. If it's a first order, a second order, a third order. And one of the ways we do that is we look at how the change in concentration affects the rate. So in this case, we can see when the concentration doubles, going from its initial 1.0 times 10 to the negative 3 to 2.0 times 10 to the negative 3. We can see the rate stays the same. In fact, the rate stays the same up to 3 times 10 to the negative 3. So since the rate is always constant in this case, m, the only way for that to work is for m to equal 1. So here m is equal to 1. I'm sorry, not 1. M equals 0. Because this concentration, this factor all, this has to equal 1. And the only way to do that is when m is equal to 0. So any concentration of ammonia brought to the 0th power is going to give you an answer of 1, or the rate is going to equal k. So in this case, we have a 0th order. That's going to be the overall order for this reaction. The rate law is kind of what I just drew up there. It's just going to be rate is equal to k concentration NH3 to the 0 power, and the rate constant k is going to equal this rate that we have up here, because when all of this equals 1, that's just k is going to equal 1.5 times 10 to the negative 6, and the units on that are moles per liters per hour. But that's how we determine these. We look at the change in molarity and we compare that to the change in rate. And depending on that ratio, we can determine what this exponent is for m. Let's try to do something like that here, where we have nitrogen monoxide reacting with chlorine. According to the equation, 2NO gas plus Cl2 produces 2NOCl gas. And they give you the following initial rates and reactions that are observed. So we have initial concentrations and the reaction rate there. So we can look at these first ones. So I'm going to label this 1, 2, and 3, just so we can get an idea of what's happening when we compare these two different things together. So if I start out comparing number 1 to number 2, we can see the concentration of NO, I'm going to put to the M, that doubles. And the concentration of Cl2 is the same. That's going to be to the power of N. So our goal is to find out what M and N are in this situation. So by comparing these, we can then also now take the rate. So I can say the rate of 2 divided by the rate of 1. I want to find out what that ratio is when we do that. So we can see that's 4.56 divided by 1.14. 4.56 divided by 1.14 is equal to 4. So that's equal to 4. So then what we need to really determine here is, since this is doubling, we're doubling the concentration, it's going up by 4. So we need to find out what order that must be. In this case, we say M is equal to 2, because when we double the concentration, we would have to square that number to get to 4. Or we can think of the, say, natural log of 2 is going to equal 2, or 4. And that 2, we have to take into account both of the two concentrations that are changing. So one of them's doubling and one of them's staying the same. So it's kind of that 2-to-1 ratio that's happening there. Going on, we also want to look at the, say, 3-to-1 ratio is the other one I'd look at. And that's because Here, between these two, oh, I'm looking at the wrong one. I want to look at 2 to 3. 2 to 3 ratio. So that's between these two. Now the NO concentrations are staying the same, but the Cl2 concentrations are doubling. So when we look at that, we can see, well, what is the difference in that rate between those? That's going to be 9.12 divided by 4.56. The rate change between those, 9.12 divided by 4.56, is equal to 2. So when the concentration of Cl2 doubles, the concentration or the rate also doubles. That's a 1-to-1 ratio. It's proportional, which means the N must equal 1 because we have that proportional relationship between those. So then we can write out what the rate law is, where the rate is really going to be equal to K times the concentration of NO to the power of 2 times the concentration of Cl2 to the power of 1. And that's going to be our rate law. So the rate constant we can then solve for knowing that. And one thing I can point out is up here in the top, notice it takes 2 moles of NO gas to do that. And that 2, well, that's very similar to the 2 that's down here. And those are going to happen pretty often there. But let's determine now our constant. So the rate, we can pick any of these to do that. If we pick the bottom one down here, it's really easy because everything's 1s. But everything's not always that easy, so I'm going to pick one that's a little bit more difficult. I'm going to pick the top one up here. You could pick any of them for this. We're just going to plug in the values that we have for those concentrations and the rates. So rate is 1.14 is going to equal K times the concentration, which is 0.50. Yeah. And that's going to be squared, and we're going to multiply that by 0.50. And we can rearrange the values here to solve for K, which is going to be 1.14 divided by, I'm just going to write this as 0.50 to the third power. So that's 1.14 divided by 0.5 to the power of 3. And I get 9.12. And that's right what I expected to get, because that's what this is here. Because if we were to plug in 1 and 1 here, that would be really just 9.12 divided by 1 to the third. So that's one way we can determine the rate constants for that is once we have the values for it, we can plug it in and find that value. So that's going to equal K. And they want to know what are the orders with respect to each reactant. Well, we determined that here and here. So I think we've solved everything here. On number 31 here, the following data has been determined for this reaction. So here we have the same thing, but it's going to get a little bit more complicated. So in this one, we have this I minus initial molar, and it's going from 0.1 to 0.2 to 0.3. We also have this OCl minus, which is going from 0.05 to 0.05 to 0.01. So notice that the iodine or iodide doesn't ever stay the same throughout it. It's always changing. So we're always going to have some rate change relative to that. But we can look at these between these first two and see that the OCl minus doesn't change in those two. So we can use that to determine what the order of iodide is. So let's go ahead and do that. So looking at stages 1 to 2, and that's going to again from 1 to 2, we can see that the concentration of I minus, it doubles, where the concentration of OCl minus is the same. So we can determine our change in the rate as well. So that change in rate from 1 to 2, there's the rate and there's the rate. So that's 6.20 times 10 to the negative 4 divided by 3.05 times 10 to the negative 4. These 10 to the negative 4s are of the same order of magnitude, so I'm not going to bother putting them into my calculator. If they were different, if it was 10 to the negative 3 and 10 to the negative 2, I'd probably have to do something with it. But now I can just say 6.2 divided by 3.05. And that gives me 2.03. Again, this is equal to 2.03. So we can see that when it doubles, the rate pretty much doubles. It's not exact, but it's close enough to say where it's not a squared reaction. It's definitely not to the 4th power, or it's not a 4 here. It's definitely a 2. So that's going to be a proportional relationship. In this case, my M is going to equal 1. Because for every increase in concentration, we get a proportional increase in the rate. Next, I want to compare 3 to 1. These two here. And I'm jumping back and forth here a little bit, mainly because I want to see these two double. But I'm looking up here, goes from 0.1 to 0.3, so this is tripling. 3 times the amount. I'm going 3 to 1, so I'm actually going backwards. From 3 to 1, so this is a third. So the concentration of I minus is a third of what it was. And then I'm going 3 to 1 for this bottom one as well, because that way my concentration of OCl minus was 5 times. It's 5 times as large as it was before. So we're increasing that concentration by a factor of 5. We're decreasing the concentration of iodide by a factor of 3, or multiplying it by 1/3. And then we can determine what our rates are. So the rate of 1 divided by the rate of 3 is going to equal, well, 1 was 3.05 times 10 to the negative 4. And 3 is 1.83 times 10 to the negative 4. We're at the same order of magnitude, so we can save that math and just do 3.05 divided by 1.83. That's 1.67. So this is kind of a weird number. Over here, the total order is the multiplication. We multiply these numbers together. So 5 times 1/3 is equal to 5/3. So what we need to do is determine, well, when is, say, 5/3 equal to 1.67 to the power of n? And we want to solve for that n. So to do that, we can take the natural log of each side. And this is pretty simple if you know your logarithms, 1.67. And you'll see pretty quickly that 1.67, then we can divide over here to find out what that value of n is. In this case, we can take the natural log of 5/3, divide it by the natural log of what we had up here. And you'll see it's equal basically to 1. And the reason why is 1.67, if I took this number on my calculator and I converted it to a fraction, it'd be 5/3. So really we had the same number there. But when you plug it into your calculator, you might not always realize that. So it's good to know kind of how to solve for it anyways, which is what I did there. Solving for that value of n, this is equal to 1. So we can see that n is going to be a first order as well. Or we can see that the total order of everything is going to be, n and m are both the same in that regard. So they're both first order, so that means it's going to be a rate then equal to K, concentration of iodide to the first power times the concentration of OCl minus to the first power. And that's by rate law. And we also want to find the rate constant for it. So again, now that we have the rate law, we can just plug in one of those rate constants. I can pick any of these to do. Let's pick number 2. Let's get rid of some of that so we can read it a little easier. So it's 0.2, 0.05, and 6.2 10 to the 4th. So writing that out, that's 6.20 times 10 to the negative 4th is equal to K times the concentration of 0.020 times 0.05. Yeah, I got that right. Okay. And these are both to the first power. That power doesn't matter in this case because it's just a 1 there. Solving for K, I can take this and divide each side by both sides. Divide that value by both sides. And we get something along the lines of this. And we solve for K. Whoa. So doing that, 6.2 e to the negative 4 divided by parentheses. Don't forget that parenthesis, because if you do, you'll end up multiplying the second value instead of dividing it. And that's equal to 6.2 times 10 to the negative 2. That's our rate constant. So we have the rate law up here, the rate constant down there, and we've solved for everything that we need. Units for this is what? Liters per moles seconds, I think. We follow the units here. We're really flipping that around. Number 36 is the next one. This one has to do with half-life, so first order decays. So in this one, we're using this equation up here, which says the concentration at any point is going to be equal to the initial concentration. So that's going to have that little 0 down there, times e to the power of negative kt, where k is the rate constant, t is the time that's passed. And this is an exponential decay. So the rate for the decay is, and they tell you what this rate is. This is going to equal that k value. And they want us to find out what is the half-life. Well, the half-life is going to be when this concentration. So if I were to divide this initial concentration over here, we get something that looks like along that lines. And when this is equal to 1/2, that's our half-life. So at the time is what we need to solve for. When is that time? When is this ratio going to equal 1/2? So we can rearrange this equation now to solve for that. And to do that, we have to use logarithms. So if we take the natural log of each side of this, the natural log of e to the power of negative kt is going to be equal to the natural log of 1/2. Well, the natural log of e to the power of anything is just going to be 1, essentially. I don't know why I wrote it like that. So first, using logarithm rules, we can pull that kt, the exponents, out front and say that's the natural log of e, which is equal to the natural log of 1/2. And this, the natural log of e, is just going to be equal to 1. So it's just 1 times kt. And then solving for t by dividing each side by negative k, we end up with negative natural log of 1/2 divided by k. That's going to be how we find the time it takes to get to half of the concentration. And that's what they refer to as the half-life. So we can plug this into our calculator because we know that k is going to equal 4.5 times 10 to the negative 2 because of this up here. Yeah. So that's going to be negative natural log 0.5 divided by, I'm going to put parentheses, 4.85. Oh, no. E to the negative 2. And there we go. That's going to be 14.3. We're in 3 sig figs. So that's equal to 14.3. And I put the negative in. And the units for that is days. Because this was in a per day unit, so that's going to flip up to the top. You have 14.3 days. That's the half-life of this. The next equation here is fluorine 18 is a radioactive isotope that decays by positron emission to form oxygen 18 with a half-life of 109.7 minutes. So now they're telling us the time it takes to get to the half that concentration. And they give us a little hint. A positron is a particle with the mass of an electron and a single unit of positive charge. It's not really relevant for what we need to know. Again, we'll learn more about that when we talk about exponential decays. And there's kind of the equation for that decay. Physicians use fluoride 18 to study the brain by injecting a quantity of fluoro-substituted glucose into the blood of a patient. The glucose accumulates in the region where the brain is active and needs nourishment. So that's just a little subnote there. What we really want to do is solve for the rate constant of the decomposition. So we know what the half-life is. We know this time is here. And we know this equation, 1/2 is going to be equal to e to the negative kt, is up there. Again, the same equation we used over here, we had to rearrange it a little bit to get to that concentration difference between what we have divided by the initial is going to equal 1/2. That brings us to this type of half-life equation here. We can then we want to find the rate constant. So we want to solve this one for k, because we have t and e is just going to be a number. So we can rearrange this, taking the natural log of 1/2, which is equal to the natural log of e to the negative kt. We can bring those negative kt out in front. So that's the natural log of 1/2 is equal to negative kt natural log of e. This is going to be equal to 1. We can then divide by negative t to solve for k. Now that we have k isolated, we can plug in that value for t, which is 109.7 minutes. So that's just going to be the natural log 1/2 divided by negative 109.7 minutes is going to equal the rate constant. The natural log of 1/2 divided by negative 109.7, that's equal to 6.32 times 10 to the negative 3 per minute. That's the rate for it. It always wants to go over there. All right. So that's part A. For part B, if a sample of glucose containing radioactive fluoride, fluorine 18, is injected into blood, what % of the radioactivity will remain after 5.59 hours? So now that we know the rate, they want to know how much is left. They want what percentage of the radioactivity will remain after 5.59 hours. So I'm going to do part B over here. So really we're taking this concentration, we're dividing it by its initial concentration, and we're setting that equal to e to the negative kt. And we want to solve for this concentration, that percentage, essentially, because since it's a decay, that numerator is always going to be less than the denominator, so it's always going to be a fraction of, and we can turn that fraction into a percent pretty easily. So just plugging in the values that we have, we know here T is equal to 5.59 hours. We know that K is equal to 6.32 times 10 to the negative 3 per minute. Now we want those units to cancel each other out, because any exponential unit needs to kind of cancel itself out to make everything work out. Especially this percentage over here should be unitless as well. So we need to convert hours into minutes. So that's pretty easy to do, because we all should know that there are 60 minutes per hour. So if I take 5.59 hours, I can multiply it by 60 minutes per hour, and I get would it be 335.4. So really T is equal to 335.4 minutes. Cross that one out. So now we can rewrite this and find out what is this concentration. This is going to equal to A, or E to the power of negative 6.32 times 10 to the negative 3 per minute times 335.4 minutes. And that should have been a parenthesis there. Minutes and minutes cancel. That gives me unitless, and I can find out what that's going to be. So E, second power, E to the X to the power of negative. I'm going to go up and actually grab this value. I don't like rounding errors, so anytime I have a value in my calculator, I use it. Multiply that by this value here, and that's going to equal 0.120. That is the concentration, or the ratio of the concentrations. This isn't quite a percent. We're going to multiply this by 100%. That's going to be equal to 12.0%. That's going to be our answer for part B. So the last part, part C, is how long does it take to take for 99.99% of the fluorine 18 to decay. So let's pick another color for this one, the green, for part C. So we wanted to get 99.99% of it decayed. The first time I did this problem, I did it wrong. I used this concentration of A over the concentration of A initial to be equal to 99.99%. And that's wrong, because that's how much is left. We need that to be away. So really, we want this to be 1 minus 0.9999. I got a ridiculous number that didn't make any sense, so I had to look back and redo it. Because we want 99.99% of it to be gone, with leaving behind a 0.0001 or 0.01%, or that's that ratio. So that needs to be equal then to E to the negative KT. We know what K is. That's going to be 6.2 or 32 times 10 to the negative 3 per minute. And then what we don't know is T. So actually I jumped ahead probably a little bit. What I want to do is I want to put this in here now. So I have the equation 0.0001 is equal to E to the negative KT. I'm going to rearrange this real quick, just so I don't have to write out that K value all the time to solve for T. So that's the natural log of 0.001 is going to equal negative KT ln of E. That's 1. So I can divide everything by negative K. That's going to be the natural log of 0.001 extra 0 in there maybe, divided by negative K is going to equal T. So now I can plug in that value for K, divided by negative 6.32 times 10 to the negative 3 per minute, which will equal T. Let's slide it over here. So the natural log of 0.0001 divided by negative, still have it in my calculator, let's use it. I'm going to enter parentheses because I don't trust the calculator to use to not do the order. Sometimes that e to the negative 3 jumps up to the top and I don't like it. So we're dividing that number. We get, this is going to be equal to 1,458 minutes. That's a lot of minutes. So how many is that in hours? So I mean, there's 60 minutes to the hour. Divide by 60. This is equal to 24.29 hours. Well, that's pretty close to a day. We still want 4 sig figs. So this would equal 1.012 days. So that's how long it would take for 99.99% of the fluoride 18 to get out of your system. Fluorine 18, I should say. So this one, number 58, has to deal with the rate constant at 325 degrees C for the decomposition reaction. C4H8 reacts to produce 2 of C2H4. And they're giving us our constant value, 6.1 times 10 to the negative 8 per second. This is going to be K. And the activation energy is this guy. That's 261 kilojoules, or 261,000 joules per mole. So we want to determine the frequency factor. So if I can say this name right, we have to use the Arrhenius. I'll spell it. Arrhenius equation, which is K, the rate, is going to be equal to the frequency factor is this A times e to the negative EA, which is the activation energy, divided by RT. So again, EA is equal to activation energy. T is temperature in Kelvin. So we have 325 degrees Celsius. We got to convert that to Kelvin. So that's going to be 325 degrees C. And I'm just going to add 273.15, the conversion rate for it. And scribble out my Celsius. So this is going to be equal to, just to make sure I don't screw that up. There we go, 598.15. Kelvin. And the R value for this one isn't the same gas constant R value that we've been using. It is the same, but it's in different units now. So now this is actually going to be in joules per mole Kelvin. And the unit is going to be 8.314 joules per mole Kelvin. We use a slightly different one here. Again, it's the same value. It's just been converted for use on this scale, essentially. So, and then A is equal to that frequency factor. This all has to do with kind of how often different atoms or molecules collide into each other. The higher the temperature, they have a higher chance of doing that, essentially. It also has to determine whether or not they're rotated in the right way, which will allow a reaction to happen. Some reactions have to happen from certain directions. So if they're not rotated in the right way, it's going to bounce off. So the more picky reactions or molecules are going to have a smaller frequency factor, essentially, because they're not going to line up correctly to have that reaction happen. But we can now take this reaction here, that equation that we have, and again we have K, I'll rewrite it here, as 6.1 times 10 to the negative 8 per second. And we can solve for what they're asking for. We want to determine what that frequency factor is. So to do that, really just a little bit of arithmetic. K divided by e to the negative EA over RT is going to equal that frequency factor. So really it's just knowing the equation to use for these things, plugging in the right values and rearranging and doing the math for it all. Because a lot of things are in the exponential, we oftentimes have to use the natural log, but not in this case. In this case, the frequency factor is not there. So plugging all these values in, that's 6.1 times 10 to the negative 8 per second divided by e to the power of negative. The activation energy was 261 kilojoules. Since my R value is in joules, I'm going to write this as 6.1 or 261,000 joules, because a kilojoule is really just 1,000 joules. Multiply that by 8.314 joules per mole Kelvin, and I'm going to multiply that by 598.15 Kelvin. Extend. So unit-wise, this is the reason I converted. The joules and the joules need to cancel out. Doesn't look like they should there because I forgot my division sign. So there should be a division sign right there. So I'm dividing in the denominator, and really I'm dividing this whole value there. So the joules and the joules will cancel each other out. The this is joules per mole, which is what I underlined here, but I forgot to write on there. It's kilojoules per mole. So again, our per mole gets to cancel out. And Kelvin get to cancel out, which is good because now I get a frequency value of per second. Per second and frequency is the right type of unit for each other. It's like a hertz. So now I can go ahead and solve this and plug it into my calculator. Now that I know I'm going to get the right units out of it, I've checked that ahead of time. 6.1 times 10 to the negative 8 divided by negative 261,000 divided by, this is where I need a parenthesis, because if I'm dividing in the denominator, I need to make sure I have that whole denominator in a parenthesis. So that's 8.314 times 598.15. Yeah, I think that's right. Wait. I need an extra parenthesis here. Nope. Insert here. Get rid of that. Insert 8. So I'm dividing, and then I'm dividing again. And what I'm dividing, there. Let me just read. I forgot my exponential. Okay, 6.1 times 10 to the negative 8 divided by parenthesis, get my exponential in there, e to the x of negative 261,000 divided by parenthesis 8.314 times 598. Oops, 8.15. Okay, that looks better. There we go. So I'm dividing by that whole exponential at the bottom, so I had to make sure I got that in there just right. And that gives me a 3.79 we'll say, times 10 to the 15 per second. So that's the frequency of the reaction. That frequency factor is equal to A. I have time for one more. This one's a really fun one. So here we have hydrogen iodide. I'm just going to run through this really quickly because I only have about 9 minutes left. But really, this is a way where we can determine what that activation energy is by using that same equation. So if we take K equal to A e to the negative activation energy divided by RT, and we got to rearrange it a little bit for turn it into a linear equation in a way, linearize it. Just so what we want to do is plot these values and then determine what the slope is for that line. And we'll get to that in a second. So if I do a little bit of mathematical rearrangement, I can say that K over A is equal to E to the negative activation energy divided by RT. Now I can take the natural log of each side. So that's the natural log of K over A is equal to negative EA activation energy over RT times the natural log of E. That becomes 1. That simplifies things a little bit. Now, logarithmic rules say that if I'm taking the logarithm of a fraction, I can rewrite that as the natural log of K minus the natural log of A. So the denominator becomes the negative value, or the second one that you're subtracting from the numerator, the natural log of the numerator, which is then equal to negative of the activation energy divided by RT. Now I can shift that ln of A over to the other side simply by adding it to both sides. That's the natural log of K is going to be equal to negative EA over RT plus the natural log of A. And now we have something that kind of resembles a linear equation where we have some value over here, which is going to be a constant because K is a constant. Or K is not a constant, but it is a constant. Either way, and this can be inversely proportional to T in this case. EA is activation energy. That should be approximately the same. And R is going to be a constant as well. So ln of A is that frequency factor that's going to be determined based off of all the different types of molecules that you have there, which ends up being our y-intercept, where it intercepts the y-axis. So we can rewrite this more as the natural log of K is equal to negative EA over R times 1 over T plus the natural log of A. And this is important because now we get this linear form where it's y is equal to mx plus b. So if we were to plot this on a graph, well, this is my y-axis and this is my x-axis. So this would be the natural log of K, and this would be 1 over T. And we should get a nice linear slope for it. So I'm going to draw kind of a slope somewhat like this. And that slope is going to have a rise over run. Well, the rise is the EA, and the run is R. Right? And it's a downward slope, so it's negative. So we can take these values in this table, because they're giving us the temperature in K, and the temperature in Kelvin, and the K constant value, and we can put them into Excel and do a quick conversion on them. So we find the 1 over that temperature, and we find the natural log of that K value, and we can determine and plot those values and determine that slope. So I went ahead and did that. Let's jump over and show you, assuming Excel can load for me. There it is. Okay. All right. So we can see over here, these are the values straight off of the table that they gave me. Okay, the temperature values and the rate values for K. And then down here, I just said, well, 1 divided by this frame, this cell, and it gave me that value. And then I copied and pasted that down to these other ones. So it's now A6 is referring to this one, and so on. Oops. So then I got that 1 over temperature column for my x coordinates. So then my y coordinates, the natural log of k. Well, Excel has a function for that natural log. So I did that function ln parenthesis, or we really have to hit that equal sign first if you're not familiar with Excel. So you hit the equal sign, you can create functions then. So the natural log of cell B2, which is this first rate up here, and then I copied and pasted that down to these other ones. And I ended up with those coordinates, essentially, created a scatter plot from them in Excel here. And then I did a linear fit. So you can always add this linear fit line where it kind of creates a line that bestly resembles all those different points on there. And I had it give me the equation for the line, which is this one down here, negative 22287x plus 25.204. And I went ahead and copied and pasted that into my other program here, so I can draw on it a little easier. So that's how I got this plot, is just using a simple Excel. It took me 3 minutes to put through everything. Most of that was fudging around with the graph in Excel, because that can always be a little bit of a trouble. But getting the data together is really quite simple. But now how can we utilize this equation? Well, like I said, that's the natural log of k is equal to the negative EA over R times 1 over T plus the natural log of A. And what this question was asking for is this activation energy, that EA. So we have the equation for that. I can say, well, that's y. So really, this EA over R, negative EA over R, is equal to this slope minus the x. This is equal to x. This is equal to y. This is my y-intercept, which is going to be equal to my ln of A. So I can say that negative EA divided by R is equal to negative 22287. And I can say that the natural log of A is going to be equal to 25.204. So just by graphing these and linearizing the results, I can solve for these problems. Remember, R is a constant, and the negatives basically cancel each other out. So EA is equal to 22287 times R. And the natural log of A, I can just take each of these to the e to the power of that. This becomes A is equal to e to the power of 25.204. So just to solve it and take it home, they're only really asking for the activation energy. This is just plug it into your calculator. You'll find out that A is equal, I did this earlier, 83 times 10 to the 10 power. And that's going to be your frequency factor, so the units for that will be per second. But for this EA, we can see that we're really taking that 22287 and we're going to multiply it by 8.314 joules per mole. And it's really joules per mole Kelvin, but since we're multiplying by temperature there, those are going to cancel out. So I'm going to go ahead and leave that off at the moment. And that's going to equal our activation energy. So the math on that says 22287 times 8.314 is equal to, that's going to be 1.85 times 10 to the 5th joule per mole. Just to get it in the right frame of things, we have joules per mole there. What are they asking for anyways? Does it say? They're asking for kilojoules per mole, which is good because when you're at 10 to the 5th power, you really want to shrink that down a little bit. We can say that's 185 kilojoules per mole because there's 1,000 joules per mole or per kilojoule. And that is our activation energy. So it's a really cool thing to do. This was a way they could determine that activation energy by making that reaction happen at different temperatures and gauging the rate of each of them. And by graphing those, we could determine what that activation energy is, how much energy is required to put into it to make that reaction happen. And that's all I have for you today. Just 6 o'clock, so Best of luck for you for the rest of the week. Tune in on Saturday. I know it might be a little after so a lot of your work is due, but on Saturday I'm going to be talking about rice tables and the different type of equilibrium equations that we can do as well. Get you all set up for Chem 223, where you start talking about acid-base reactions, and you're going to need those rice tables when you get to 223. So definitely chime in there. Have a great day, and if you have any questions, on Saturday also I'll have drop-in tutoring hours just after my live stream up until 5 p.m. Again, my live stream's at 2 p.m. And you can also schedule a tutoring appointment with our chemistry tutor Amir in the Penji app. Have a great day and enjoy.